This video is a simple overview of ezRA. ezRA is short for ezRA, which again is short for Easy Radio Astronomy. The professionals say our Milky Way galaxy looks like this from above. The galaxy has a very busy center with spirals of stars coming out from the center. Our sun is here about 2/3 of the way out from the center. Plotting my radio astronomy data seems to show similar arcs of galactic hydrogen. This is the picture from above. From the side, the galaxy looks like this, a flat plane. How is this done? How can you do the same? First, we talk about the hardware. A radio antenna delivers its energy quickly to a low noise amplifier, which sends radio frequency energy down a coax cable to a receiver, which is plugged into a PC. That PC could be running Windows or Linux. The PC records the data. This particular SMART-T receiver is convenient because it sends 4.5 volts DC back up the coax to power the low noise amplifier. The antenna could be big, like this 15-foot dish, or smaller, like this 3-foot Wi-Fi grid dish, or even simpler, like this Yagi antenna, which is mostly 11 wires stuck in a PVC pipe. We can see the low noise amplifier in a plastic bag down here. Bigger antennas work better, but much can be learned from small antennas. This is that low noise amplifier that was in the bag. I like this bare bones version that gives access to this 4-pin connector to provide more control. This LNA currently costs about $40 US. Here is that SMART-T receiver that powers the low noise amplifier. It is about the size of my finger and plugs in the PC. This receiver currently costs $34 US. Okay, it's time to hook up the hardware and collect some data. We need some software to control the receiver and record data to computer files. There are many methods. One of them comes with ezRA. That method is called EasyCol, EasyCOL, with COL short for collect. On the left is the latest data sample. After averaging thousands of readings, it produces one sample, maybe with 256 values, shown by a series of red dots, each at different frequencies. EasyCal calculates the average power value and presents them in 3 strip charts. The bottom strip chart shows that average power over the last 24 hours, from long ago on the left to most recent on the right. The middle strip chart shows the average power over the last 1 hour. And the top strip chart shows the last 500 samples. These strip charts often show the effect of temperature on the system power values. The data starts about 7 o'clock in the evening and shows as the evening cools, the recorded power levels increased until 6 o'clock in the morning when the sun came out, warmed the day, until about 2 o'clock in the afternoon when the clouds came in. EasyCol records all those values as numbers in a computer file. ezRA can analyze those data files. We can represent each sample as a vertical line of 256 values and line up all the samples in order like books on a bookshelf. The higher values have a brighter yellow color. On my display, I can see a faint yellow line slowly wiggling across the screen once a day. The software does its magic and highlights that faint galactic hydrogen signal. Now we can see a hydrogen snake slowly wiggling across the plot. I see 2 parts of the day with brighter energy. Let's plot that data on the radio sky. First, we talk about RADEC sky maps. RADEC is short for right ascension and declination, the names of the 2 coordinates. Right ascension is the horizontal coordinate from 0 to 24 in hours. Declination relates to the Earth's latitude and so has values from -90 to +90 in degrees. All the stars and their constellations can be shown on one plot. We can also see the Milky Way galaxy as this bright path of stars across the sky. Those same coordinates describe the radio sky, here shown with the power at 400 megahertz. Again, the Milky Way galaxy is this bright U-shaped path across the sky. Here in the northern hemisphere, if we point the antenna facing south at about 45 degrees up from the horizon and record the data while the Earth rotates for 24 hours, we might get data like this. We record data for a horizontal line across the sky. In this vertical offset plot, we can see the data started over here on the right, got a little louder in a certain part of the sky, got a louder again in a different part of the sky, went to the end of the plot and started another plot for the next day. The brighter bumps of power seem to align with the galactic plane. That was recording one drift scan, but we can record many more with each drift scan with a slightly different elevation of the antenna. Again, the bumps in the data seem to align with the galactic plane. The program can assign brighter colors to the higher values. And the ezRA software can smooth that data. We can also plot the radio sky on galactic coordinates. Here is the galactic plane across the middle here, with the galactic center at 0, 0 in the middle. We have the galactic longitude coordinate increasing from -180 to +180, increasing to the left. And the galactic latitude coordinate goes from -90 up to +90, increasing upwards. But this plot represents the view from inside a sphere, and this top line is actually all one point, as if pulling a belt through the top line of points. We can represent the sky with a sinusoidal plot. But the professionals don't like that sharp point at the top and the bottom. So with more math, ezRA can plot the radio sky with a Movida projection. But 2 areas of this plot have no data. Up here near Polaris, the North Star, there is no data. And the telescope could not see this area of the sky because the Earth was in the way. The computer does its best to predict, but the data in those areas is misleading. so ezRA can mask out that misleading data. And a graphics editor can fill those areas with whatever color you choose. That same data includes velocity information. Velocity can get complicated. Consider the sun in its neighborhood of stars, all revolving around the galaxy. At the same time, the Earth is revolving around the sun once a year. And the Earth is rotating around its north-south axis once a day. Those three motions can be calculated and removed from consideration, leaving only the velocity of the hydrogen gas with respect to the neighborhood stars. Looking at one spot along the galactic plane, we might find one cloud of hydrogen with no relative velocity. In another part of the galaxy, we might see two clouds of hydrogen with different velocities with respect to the local neighborhood of stars. Or three clouds of hydrogen. Or maybe four clouds. There are 360 degrees of galactic longitude, and each has a slightly different view of velocity. If we stack all of them up like slices of bread, they start to look like a range of hills. And we start to see patterns. Rotating this plot 90 degrees counterclockwise and representing the highest hills with the brightest yellow, we get this more traditional plot. And we finally get back to the galactic arms. Here is the professional's view of the galactic arms from above. And when ezRA plots that previous data differently, we get this plot. Do you see the arcs of brighter data? Here is my suggestion for labeling the galactic arms. Does the data support my labels? You can do this too. Please give ezRA a try and send me news of your successes.